me if I run short. But we're going to finish up the material in Chapter 5, and then starting next week, we'll break into Chapter 6, talking about analytic functions. So we're going to quickly do a follow-up to the Fourier series, and then we're going to expand the horizon. So first of all, these will be extensions, but also in a way of reminders. So for Fourier series, we exactly worked with the interval functions defined over the interval from minus pi to pi. So we defined everything on the interval from minus pi to pi. And of course that made everything super clean, but it's actually rather trivial to generalize this to an interval from minus L to L. And when we do that, the basic only difference is what's going into our exponent. Sorry. Where the Cn coefficients in this case are given by 1 over 2L to the 1/2. Integral from minus L to L of fx e to the minus I n pi x over L dx. Okay? Obviously, you could just set L equal to pi, and this will reduce back to what we got last time. Or alternatively, we can shift it from a symmetric interval to a non-symmetric interval just by adding a displacement. Case, the coefficients end up being once again 1 over 2 pi to the 1/2, and I go from minus pi plus d, pi plus d. Okay? And given that you can shift those, you can now take it from any interval with any beginning to any end that you want. Okay? By combining those two effects. Now, if the function that we're trying to approximate with the Fourier series, if it happens to be an even function, then you'll note that the Bn coefficients all work out to be 0. This is the Bn's in the original sine-cosine reduction of the Fourier series as opposed to the complex exponential. So you have Bn are the sine coefficients and an are the cosine coefficients. So if you're dealing with an even function, the Bn is 0, so you end up with a cosine in x series, which is obviously the even series of trigonometric functions. And if it's odd, the an is equal 0, and you end up with a sine in x series. Okay, so that's sort of trivial stuff. And then just to kind of finish out the story, in parallel to the stories that we told for the Hermite polynomials and the Legendre polynomials and the Legendre polynomials and so forth and so on, we might ask, what is the differential equation satisfied by these functions? Well, Andrew, what differential equation is satisfied by these Fourier functions? Well, I mean, this is the most important part of it, the exponential of an imaginary of I times an integer times pi times x. Just take x. So if you take the derivative of that function, does that function remain?
Yes.
Okay. If you take the second derivative of that function, does that remain?
Yes.
Yeah. So the second derivative with respect to x squared of one of these functions u is equal to what?
U is
So just take one of these.
right.
So it's just going to be something like minus n squared times u. That's the generic form of it. There's a normalization with respect to pi and so forth and so on, but okay. All right, it's a really simple differential equation is the point, compared to all of the other differential equations that we encountered in the Sturm-Liouville story. Okay, so now what we're going to do is we want to kind of break out of the bounds of these finite closed intervals, okay? Because after all, this is telling us, did you finish? Are you going to keep your glue?
You can have it if you want.
I don't want it. You can have it back. Okay, I might take it and hang it up in my office. It's just been in my backpack forever because I've been trying to bring it and give it back to you every time, and you've missed the last 2 lectures. But anyway, okay, so these Fourier series, they obviously approximate functions which are defined over these finite intervals, but we'd really like these intervals to be infinite. That way we can work with functions which have an unlimited range. And the obvious choice in doing so is to take L to infinity in this scheme, right? Right? Why not?
You're dividing by L. Why do you want to
Oh, shit, yeah, we're dividing by L.
I don't want to do that. I also vote that we don't do that. Yeah. That's okay if it's fine.
Okay. Okay, yeah, you can't fix Fourier functions in order to go from infinity. All right, we'll move on. No, I'm kidding. Obviously you can. Obviously you can. Okay.
That's why we were short.
Oh, hold on. Okay, here we go. So in order to work this thing up, in order to take the limit as L goes to infinity, we're going to do some redefinitions. So our first redefinition is going to be a rescaling of x. Okay? And then we are also going to do a rescaling of n pi over L to the 1/2. And we're going to call that Kn. Okay? Which I guess I should have, here, I'll do this. Okay. These two together are going to allow us to replace n pi over L x, which is the thing that's sitting up here, with what? Zan. You. I just pointed at you, Zan. What can we replace the exponent, the factor of n pi over L times x with, given these redefinitions? Hold on. Oh, shoot. Sorry, my volume was off.
You're good.
Yeah, say it.
I
Well.
was just calling for help. I don't know.
Oh, okay. Anybody want to help her out?
I think it should be K and Y.
Yeah, K and Y,
Thank you,
exactamente.
Joe.
Okay, obviously. All right. Now that's our first redefinition. Now we can also take pi over L to the 1/2, and we can recognize that that is just Kn plus 1 minus Kn. that make sense? Okay? And so we can call this thing delta Kn. And then we can say that dx is L over pi to the 1/2 dy. Okay? So unloading all of this into these two expressions, we get the following. F of y is 1 over 2 pi to the 1/2 sum over Kn from minus infinity to infinity of g Kn e to the I Kny times delta Kn. Okay? Are there any questions about that? Yeah.
Nope. I'm good.
Yeah, everything cleans up.
Okay.
Everything cleans up nicely. You've got this 1 over 2 L to the 1/2 factor, and you're replacing that with a combination of these things, and that's generating this 1 over 2 pi to the 1/2 and this delta Kn factor. Okay? Now, these coefficients can be given by the following expression. Everybody on board? So now we're in the time and place to take L goes to infinity. Okay? So most importantly, if we take L goes to infinity, these steps delta K are going to become vanishingly small. Okay? We were summing over the delta K's. So in this limit, the sum over delta Kn becomes what? And I'll ask a person to give me the answer. Madison. Madison. Yes, you're there. Really? I asked you a question, I think. Are you going to give me an answer? Hopefully she's typing out an answer. Total transparency, I stepped out for a second to absolutely not. Okay, I'll just pick another person. Josh.
Is it Kn?
What does the sum over delta Kn transition into when the delta K's are becoming infinitesimally small? What do you think?
I still want to say it's Kn.
Kn
Yeah. Sounds like an integral.
of over?
Over Kn, dKn.
It's an integral over dk. Okay?
Why no n?
What the so the
Yeah, because yeah. What if he?
yeah, so you're not summing over n here, you're summing over delta k, and delta k is going to
Why does
0.
mean why not dk sub n?
Say it again?
dk subscript n.
N is becoming irrelevant.
Yeah, that was my thought.
Yeah, n is becoming irrelevant. I mean, this is an addition of each value of k with respect to the next one and the next one and the next one. They're just no longer separated by some discrete quantity. They're infinitesimally close. So that's what the integral sign means.
Well, what are the bounds on that?
Huh?
The bounds on the integral? Negative infinity to infinity.
Yeah, they'll go from negative infinity to infinity. Okay? So let's write down what these finally come into. So we get Fy is 1 over 2 pi to the 1/2. Integral from minus infinity to infinity of gk e to the I ky dk. Whoops. Sorry. And then for this guy, we get look familiar?
Yeah, it's pretty nice.
What is it?
The Fourier Transforms.
Yeah, these are Fourier transforms. That is, two functions that are related by this set of relations are Fourier transforms of each other. Okay? So it just turns out that wanting to generalize the Fourier series to an infinite interval naturally leads us to the Fourier transform. And I just want to go ahead and point something out because I promised a few lectures ago that I used a result which we hadn't learned yet, but we would be learning later on. And now I want to revisit that result. And you might or might not remember this, but in the Sturm-Liouville theory, we found that we had a function g of k, and it was the integral from minus infinity to infinity of f of x, wx, e, oh my goodness, why did I write that? E to the minus kx dx. And it equaled 0, and I argued that this implied that f of x wx equals 0. Can you see it now? Okay, that's fine. So if this is equal to 0, but I want to know what these are, I just integrate this gk. But gk is 0, so this is 0. Okay? All right? Okay. So now let's review a couple of facts about Fourier, and then we'll move on. First of all, just for shits and giggles, let's shove G into F. Just go up to him and push him. Get in there! Anyway, if we do that,
So aggressive.
huh?
You're just gonna cancel out everything?
Yeah, pretty much. Let's do it. So we're going to get 1 over 2 pi, the integral from minus infinity to infinity of the quantity, which is the integral from minus infinity to infinity of f of y prime, e to the minus I k y prime, dy prime. I don't want to use y again because I don't want to get my y's confused. E to the I k y dk. Okay? Now I'm going to play that old trickery game where I just interchange the order of integration. Which we know we can do if we're basing things on a Lebesgue measure. But actually also because of what the result is going to be. Okay? So if I interchange the order of integration, i.e. I do a switcheroo, what I find is the following. I'm actually going to drag this inside. that seem reasonable? What is this?
Correct.
It's a delta function. It has to be, because this is the integral over fy prime, and it's giving me fy. So this is yet another way to define the delta function. Okay? And the swapping of integrations is gently tied into the fact that this is not a function itself. Okay, it's a distribution. All right, now we can also, and let me do this. We can also ask, all right, fine, if I've got Fourier pairs, then how is the integral of the magnitude of fy, this is the magnitude squared, how is that related to the integral of the magnitude squared of g? Well, let's see. Okay, I can just use this expression here. Shove it in twice. Nope. Okay? And then once again, we can do the old switcheroo. And what we get is the following. All right. Massaging this just a bit more. What is this?
Delta again.
Say it again?
Delta function.
Yeah, it's a delta function.
K minus K prime.
Exactly. Okay. All right, one last note on the Fourier stuff, and then we will move on. And this is an answer to the question. If I have functions which are Fourier transforms of other functions, say I have two of them, f1 and f2, and their Fourier transforms for g1 and g2, what would the Fourier transform of f1 times f2 be? Would it be the Fourier transform of f1 times the Fourier transform of f2?
I feel like you can't do that simple.
Right, well, these definitions involve calculus, and you have to remember that with calculus, you don't get that simple distribution of anything, okay? Same with integrals. Okay, so let's explore what happens if I try to do the Fourier transform of a product. So I'll call the result GK, 2 pi to the 1/2 integral from minus infinity to infinity of f1y, f2y, e to the minus ik y dy. So this is the Fourier transform of the product of functions. Okay, and I'm claiming I know there are separate Fourier transforms. Okay, so here we go. 1 over 2 pi to the 1/2 integral from minus infinity to infinity of, and now I'm just going to do this guy in terms of his Fourier transform. And now I'm going to switcheroo again the integrals. And in doing so, I'm going to get the following. Okay. What is this?
Direct delta, yeah.
No?
No? Okay. Is it, I don't know. It's F2 of G, no?
Well, let me kind of.
Should be. Yes, please do. Yes, I mean, yes.
I mean, this looks a lot like the Fourier transform of f2y, except for that k prime minus k.
Maybe it's G2 of K prime minus K.
Exactly. Okay, and this is called the convolution.
I've heard that word before.
Yes, yes. So the Fourier transform of a product of functions is the convolution of the Fourier transforms of the separate functions. Okay? If you follow this in the book, he does it the other way around. He starts with the convolution and it works backwards and says, oh wow, this is the Fourier transform of a product of functions, which I thought was kind of ridiculous. At any rate, okay. So clearly Fourier series are not restricted to live in one dimension. They can live in many. And the generalization to as many dimensions as you like is rather straightforward. In d dimensions, what we have is the function of the position vector r, which is just replacing x with its multivariate counterpart, is going to be 1 over 2 pi to the d over 2 times the integral from minus infinity to infinity to the d power. I'm not going to write d integrals. There's d of those. That's what I mean. Times g of k e to the I k vector dot r dk with dk equaling dk1, dk2 up to dkn, or sorry, dkd. And then g of k is, of course, just the Fourier mirror of this. And then in this story, we also again get the higher dimensional generalization of the delta function. Okay? And this delta function is going to be evaluated by the integral. Okay? So you can do this in any number of dimensions that you like. Now, we are going to take the Fourier story and we're going to bring it into 3 dimensions, but we're not going to stick straight to Fourier. Okay, we're going to cheat a little bit, and we're going to get a different set of results. But before I go into the details of that, I just want to remind you of the program that we have been following. And this is one of the more important things, one of the more important takeaways from what we've been doing. And we'll do it again in what we're about to do. So, first, we use Weierstrass to argue that if f of x is continuous on a closed interval, a to b, there exists a sequence of polynomials such that the limit as n goes to infinity of this sequence gives you f of x with uniform, hence also mean, convergence. Okay? And then what we do is we take the set of polynomials that are in this Pn. So we take the linearly independent set of polynomials and GS it, Gram-Schmidt it, for an orthonormal basis. That's my new symbol for orthonormal. I was pretty smart with that.
Looks like a bishop in chess.
Yes, it does. Then Pnx can be written as the sum of the superposition of these orthonormal polynomials where the coefficients depend on n. Okay? And now what we do is we prove the completeness of this basis, all right, by proving its closure. And the argument for the closure goes the same way. We say if Fqn equals 0 implies that Fn equals 0, then this also implies that Fpn equals 0. But we know that Pn converges in the mean to F, which we can say is that the magnitude of F minus Pn is less than epsilon. Hence, using the fact that these are orthogonal, we have that this inequality becomes the magnitude of F squared plus the magnitude of Pn squared is less than epsilon. But we can take epsilon to be as small as we want. This is the sum of two positive things, and so F goes to 0 almost everywhere. Okay. Now, since the Qn are complete and orthonormal, then that means that we can write Fnx as the sum from I equals 0 to n of Ci Q Ix, where these do not depend on n, which tells me that you have mean or convergence in the mean to the function f of x. If I take the infinite limit. Okay, so that's the story that we've been seeing repeated over and over again in a broad outline. And again, we're going to play through it in the case that we're about to look at, and this will be the last one, okay? So what I want to do is I want to repeat the trickery that I used to get the Fourier series. So I don't know if you remember, but we started by using Weierstrass's extension to a polynomial of multivariables. In fact, we just focused on two, x and y. Okay, but we restricted x and y to the unit circle, and that allowed us to redefine x as cosine theta and y as sine theta, and that development eventually led us to the Fourier series. Okay? What I want to do now is the three-dimensional version of that. Okay? So here we go. First of all, for Weierstrass, we know in 3D that we have the limit as capital M goes to infinity of F capital M. I'm going to do my best to make my capital M's look different than my little m's. Yeah, that's right. Of the sum of M n rho equals 0 to capital M of the coefficients C, M, n rho, which depend on M, x1 to the M, x2 to the N, x3 to the P. Yeah, I'll do P dot rho. Okay?
You
What?
did your best, but
Huh?
distinguishing between the uppercase and lowercase m's.
Yeah, so this is,
Lowercase, the other one is that superscript, a capital. Yes.
okay, I'll make this like a jagged tooth.
Got it.
How's that? Yeah, you're damn right it's good. Awesome. With uniform and mean convergence. Okay?
Is the superscript a label?
Huh?
Is the superscript just a label?
It's just telling you that these coefficients would change if you change the value of m.
Okay.
That's very different than if you're doing a series, because like, take a Taylor series. If you go further out to get more accurate in the Taylor series, the coefficients in the earlier terms don't change, but this is different, okay? All right, so this is largely the first step here. And now what we're gonna do is we are going to, and these are just x to the, these are the x1, x2, x3 are just the 3 coordinates of our 3-dimensional space, and then these are just polynomials, so the x's are raised to different powers, okay? What we're going to do is we're going to introduce a new set of coordinates. So z1 will define as x1 plus I x2, z2 is x1 minus I x2, and z3 is x3. Okay? These aren't the best. We can do better. How about I call z3 r cosine theta. I call z2 r sine theta e to the minus I phi, and I call z1 r sine theta e to the I phi. Just transitioning the spherical polar coordinates, where of course phi goes from 0 to 2 pi, and theta goes from 0 to pi. Okay? Now, this is a polynomial in the x's. If I took all of the x's in this expression and replaced them by the z's, so I could solve this. x1 equals blah, 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 is 1 over 2i, z1 plus z2. Then the resulting expression would be polynomial in the z's, right? So we can say that fr equals the sum over alpha, beta, gamma equals 0 to m of admittedly new coefficients okay? But now we can just plug in these expressions here for the z's here. I'm going to do a little bit of rearrangement in this final expression, but it should make sense. Okay? Is everybody on board with that?
Did we constrain alpha, beta, and gamma just now?
Yes?
Were they before?
Think about it. So where does this term come from?
There are three Z's.
There are three whats?
Z's.
There are three Z's, each Z's got an R in it, so you get R, and it's going up to the 3m power, okay? Where did this term come from?
Z1, Z2.
Yeah, it comes from the Z1, Z2, where this has got the alpha and this has got the beta in it. Where did this term come from?
Also Z1 and
Same thing, just with the signs.
Yeah. And then this term?
This Z3 plus.
Okay. Why do you think alpha plus beta plus gamma has to be L? Oh. Look who's on top. Joel.
Okay. So if you substitute Z1, Z2, and Z3 into the thing, you're going to get an R.
Well, you're going to substitute in R to the alpha sine alpha theta e to the I alpha phi. Right?
Yeah.
I don't have an answer to the
So-
question. The R in your expression, should that be R to the L or? I don't know where this.
Oh, sorry. Yeah, that should be R to the alpha.
Oh.
My bad. My bad.
Makes a little bit more sense.
Yeah, sorry. Okay, good.
So then you're going to get R to the alpha plus beta plus gamma. So you can make that R to the L. And then there's like a combinatoric, sorry, hard word. There's like a number aspect to this that I don't know how to prove, but you're covering all the same things. When you do
Yes.
that sum as you do this sum.
Okay. I mean, he obviously pointed out, you're going to end up with R alpha plus beta plus gamma, but we're defining that to be L and letting L go over that range, but then the alpha, beta, and gammas have to satisfy this, and then we're letting them sum over that range. Okay? I mean, think about it. You're summing over 3 indices here. Here you're summing over 4. There shouldn't be the freedom to sum over 4 indices. But there's not, because you have this one restriction. Okay? Now, if that was not a headache, this is going to be a headache.
Yes.
All right? We're going to do some relabeling. And this is where it gets really ugly. But in the end, it'll be really pretty, I think. All right, here we go. I hope you wrote down the method. Okay, so what we're going to do, just like with the Fourier method, okay, when we were deriving the Fourier series from the Weierstrass result for polynomials, we're going to restrict to r equals 1, and we're going to relabel alpha minus beta equals little m. Okay? And this little m is going to play an important role. Now, we know that alpha, beta, and gamma are greater than or equal to 0. Okay, these are polynomials in Z with positive powers. Therefore, and again, this is going to seem silly, but it'll pay off in the end, alpha plus beta, which is just m plus 2 beta, is greater than or equal to 0. Okay? And alpha plus beta is greater than or equal to alpha minus beta magnitude, which is, of course, the magnitude of m. All right? This should hopefully be obvious. And then this tells us that alpha plus beta minus the magnitude of m, which is m minus the magnitude of m plus 2 beta, is greater than or equal to 0. And now here we go. If m is greater than 0, then m minus m equals what?
0.
0. Yeah, it's not a tricky question. 0. Okay? If m is less than 0, m minus m is what?
2m.
It's 2m, yeah, which I could just as well write like that. Okay? And now we can take this expression and we can rewrite it, and we can now say, well, in the positive case, we have alpha plus beta minus m is equal to 2 beta. Okay? And in the negative case, we have alpha plus beta minus m is minus 2m plus 2 beta. Okay?
Wait.
So these expressions are here, but they're equivalent to this, and all I'm doing is I'm plugging in these results into here. Okay? What can you tell me about the results that might be important?
M equals 0.
Nope. It's going to be 1/2 later on. M, B, they're all integers. So these are,
Integers.
they are, okay, I'll pick a card. Dang. Sophia, I'm going to ask you this question in a very cryptic, loaded manner. Are you ready? 2 times this, 2 times this, 2 times this. What's the result going to be?
I don't know what you're pointing at, but I'm gonna assume it's times the thing.
Say it again.
Where are you pointing? In the what on the whiteboard? Where is that on the notes? I can't see what you're pointing at.
Right there. Oh my God.
So if 2 times that.
They're even. Yeah.
Oh, it's just an even or not.
I'm not asking
Also
tall.
integers, though. They are also. We did
Yeah.
say integers,
Yeah.
so we should get at least 99% of the credit for that.
Yeah. No, but I want to know which integers. That's gonna be important in just a minute. Anyway. Okay, here we go. All right, now here we go. So we can take the sine of alpha plus beta, theta, cosine gamma of theta, and we can rewrite it as follows: sine of alpha plus beta minus the magnitude of m, theta, sine of the magnitude of m, theta, cosine gamma theta. Okay, all I did was I put in a sine m here, and that's canceled by the sine minus m here. All right, so this we can write as sine squared theta to the 1/2 alpha plus beta minus m sine magnitude of m cosine gamma theta. Whoops. Okay, this is really just me putting in a 2 and a 1/2 that multiply together to give me back what I had here. Okay. Well, we can take this and we can rewrite it. It's 1 minus cosine squared theta to the 1/2 alpha plus beta minus m sine of m theta cosine gamma theta, which we will call sine of m theta times FLM cosine theta, where FLM cosine theta is a polynomial in cosine theta of degree what's the degree of this polynomial? Max, are you there?
Yeah, I'm here. I'm just trying to find where you are in the notes again.
I am right here.
84.
And your question was the degree of a polynomial?
Yeah, what's the degree of the so this is a polynomial in cosine. It's various cosines to factors, but what's the highest factor? What's the degree of this? Or what the highest exponent?
L minus n.
Well, yes, that's jumping to the short case. So the highest one is cosine squared to this power. Okay?
Yeah.
So that's cosine to the alpha plus beta minus m plus gamma. So that's to the alpha plus beta plus gamma minus m, which is L minus m.
Sure. Yeah, that makes sense.
Okay? All right, now, let me see what I can erase. I can get rid of most of this. So this is, of course, why the alpha plus beta minus m being even was important. Okay? We'll get rid of all this garbage. Now, we would prefer to use this m as our label, but if we're going to use m as our label, this summation we have to rewrite. Okay? So here's what we can say. First of all, we can say m is defined as alpha minus beta. This is less than L. Since, of course, alpha plus beta plus gamma equals L. Does everybody, okay, so does everybody buy this, that alpha minus, so alpha, beta, gamma are all positive, and I'm arguing that alpha minus beta is less than alpha plus beta plus gamma. Does everyone buy that, or do you need me to prove it to you?
I'm good. Right.
You buy it?
Yep.
Okay, good, all right.
How much? I'm broke.
This immediately tells us that L minus the magnitude of m is greater than or equal to 0. Okay? But that means that the magnitude of m is less than or equal to L. So this means that if we want to write this in terms of m instead of the alpha, beta, gamma, we get the following expression. Sum from L equals 0 to 3m. Sum from m equals minus L to L. Okay? Of B, L, M, M, e to the I, M, phi, sine, M, theta, F, L, M, theta, cosine theta. Okay? which we will redefine to be sum L equals 0 to 3 m sum little m from minus L to L b m L m y bar L m of theta and phi. Okay. Just taking all that junk and calling it y bar. Okay. So I've got these functions over which this sequence is defined as a superposition with coefficients which depend on how far I'm taking the range. Okay. This set of functions is not necessarily orthonormal, so we can Graham-Schmidt it to get its orthonormal form. All right. Doing so, and again, I'm following the steps in that overall procedure which I wrote up earlier. If we Graham-Schmidt this bad boy, first of all, we're going to need an inner product. And actually, if I Graham-Schmidt this, I'm going to get what are called the YLMs, theta and phis. And what we want, of course, is that YL prime, M prime, YLM, which is going to be defined via the inner product in 3 dimensions over the surface of a unit sphere, because we're working with r equals 1. This is going to be an integral of YL prime, M prime, star YLM over the solid angle.
Alex, I have a question.
Yeah.
So, in our process when we do this, the y bar, we use that Graham-Schmidt to orthonormalize a basis. What is y bar a basis of?
So this is a linearly independent set, but it's not orthonormal. And we're going to normalize and orthogonalize that using Graham-Schmidt here. This is what we're going to do.
Yeah.
Here.
So we don't have a basis yet.
No, we don't have an orthonormal basis. We have a basis because these are linearly independent.
Yeah, but what's that basis? I know it's spherical harmonics, but what is it a basis of?
Well, these aren't spherical harmonics yet. They'll be spherical harmonics once we've orthonormalized them. This is just the linearly independent set that comes from the Weierstrass theorem. Okay? All right. So, I mean, I had expressed, well, I mean, that's the expression for it right there. Okay? So let's orthonormalize these. So this integral over the solid angle is, of course, integral from 0 to 2 pi, integral from 0 to pi of sine of theta, y L prime M prime star, y L M, d theta, d phi. And what we, of course, want this to be equal to is del M L, or del L, delta L prime L, delta M prime M. Okay, this is the definition of the orthonormal set through the inner product. Okay, so we'll start with y bar of 0, 0. So recall that this guy, this FLM, is a polynomial of degree L minus M. So what's the degree in this guy? 0, okay? Polynomial of degree 0, it's just a number, okay? So we could just call this the number C, and then we normalize it. we get that y0, 0 is 1 over 2 root pi. Okay? Now, if we want to do, so this is the L equals 0 case. If we want to do the L equals 1 case, what are the allowed values for m? For m.
Negative 1, 0, 1.
0 and plus or minus 1.
Yes, exactly. So we have m equals 0, m equals minus 1, and m equals plus 1. If m is equal to 0 and L is equal to 1, what is the degree of the polynomial f10? It's 1, okay? So we can write this as a plus b cosine theta. What is the degree of the polynomial when m is minus 1? It's 0. So this is again a constant. And when it's 1, it's also 0. So again, that's a constant. Okay? All right. So we have immediately that y bar 1, 0 is a plus b cosine theta. Y bar 1 minus 1 is e to the minus I phi times sine theta times c. And y bar 1, 1 is e to the I phi sine theta d. And you're just putting back in the e to the I m phi's and the sine m thetas. Okay? Now, if we want to find the normalized and orthogonal y10, okay, then you know how this goes. We take y bar 1, 0, and we subtract out the one we already have, times the inner product of that with the one that we're trying to fix. Okay? This is just Graham-Schmitting. All right? Now I'm going to skip the details, they're in the notes. But if we do this, we're going to end up with square root 3 over 4 pi cosine theta. And then if we do y11, we get minus root 3 over 8 pi e to the I phi sine theta. And y1 minus 1 is root 3 over 8 pi e to the minus I phi sine theta. Okay? What are the y's? What are their names?
Spherical harmonics.
These are the spherical harmonics. Okay? Now in the notes, I go over how we play out the rest of the story. Okay? How we prove that this orthonormal set is actually complete. We use the same procedure that I gave in the outline. Okay? So in the end, what we can say is that a function of R is convergent in the mean to this expression. Okay? Now, I want to take a minute and I want to talk about these spherical harmonics for just a moment, just to make sure that they make sense. What is a sphere?
Round circle with extra circles.
It's a circle with extra circles? No, it's not. What's a sphere? A two-sphere. That's what we're working with here. These spherical harmonics are functions over a two-sphere, a unit two-sphere. What is a sphere? And I liked your idea of circle over circles, but it's not circle over circles. What is it?
It's a volume defined by,
Well, let's say it's something over something. What do you think?
Is it just the magnitude of the function has to be constant over?
No, I'm talking about the geometry. What is a sphere?
It's just a constant radius.
Yes, I agree. I totally agree with you.
that's good. What do you want us to say?
The set of points equidistant from one point.
But that's the,
A set of circles whose
Are we
radius
saying-
is a circle?
What if I considered a line,
are we defining the sphere as its?
and at this end of the line, which I call -1, and at this end of the line, which I call 1, I have a circular radius 0. If I go to the right a little bit, I get a circle which is bigger. If I go to the right, I get another circle which is bigger. And the story plays out such that if I hit the middle, I get a circle of radius 1 or 2, or no, radius 1. Anyway, and I'm sorry my proportions are not working out. I tried to draw this in my notes, and I ended up having to use all this shit to construct it.
It's beautiful.
It's actually pretty in my notes. It actually works out, see?
Yeah, it's great.
It's great, isn't it? It's nice. Look at the notes, folks. That's where your power is.
The circle of circles is what it is.
That's what I said.
No. This is a set of circles over a line. Okay?
Is that like a trimetric view or something? Isometric?
It's just a way of breaking out this two-dimensional surface into one-dimensional
Okay.
configurations.
Okay.
Here's the important observation. If I play this story out for the circles, what do I end up with?
You end up with basis.
And what do we call it? What's the name of it?
The spherical coordinates.
No, if I just take a circle and I play out this entire story on a circle of any radius, but if it makes you comfortable, the radius 1, what do I end up with at the end of the story? We did this last time and partly today.
Fourier functions.
We end up with Fourier functions, right? What if I do a line, say from -1 to 1, what do I end up with? What do I end up with if I play out this whole story over functions defined on a line interval from -1 to 1?
Is this still Fourier just without the R?
Nope.
So what would be the?
Any takers from Zoom? If I play out this entire story for functions defined on an interval from -1 to 1, what do I end up with?
Legendre modes?
Exactly.
I was thinking how I could have made a word.
So if you think about it, the surface of the sphere should somehow just be integrating the Fourier story with the Legendre story. It turns out that you can easily recover the Legendre story by what in here, what would I take to be 0 in this part of the story in order to recover the Legendre story?
The phi.
The phi.
And then the cosine.
And how do I remove the phi part of the story?
How do you remove it?
Yeah. You set what to 0?
The phi.
Oh, no. Set m. You take the m equals 0 term in here. Okay? So if I take the m equals 0 term, then phi drops out, and I'm just left with a function of cosine theta. Right? So here's the emergence of this. First of all, there is a Rodriguez formula for the spherical harmonics, and it takes the following form. I'm writing in blue. Okay? You can use this Rodriguez formula to generate any of the spherical harmonics YLM. What is this? This is an associated Legendre polynomial, which we briefly talked about at the end of our discussion of the Sturm-Liouville. But if I take m equals to 0, what do you think that is?
Just Legendre.
It's just a Legendre polynomial. In fact, if I take m equals to 0, oh wow, 2L plus 1 over 4 pi P L cosine theta.
Did that one half.
Sorry, say that
The
again?
square root, you forgot the square root.
Oh yeah, sorry, square root. Okay, so if we ignore, or if we ignore by setting m equals to 0, the circular part of this two-dimensional geometry, we're just working with a line interval. We're parameterizing where we are on the line interval, not by x from -1 to 1, but rather by cosine theta, but who cares? So we just end up with Legendre polynomials in cosine theta. Okay? Can we ignore the line part of the story and just focus on a single circle?
We make our interval just 0 to 0.
No, it won't work. You can't do it. Okay? All right, that's it for today. Hope you come on Thursday, ready for your exam. Again, you should expect